So in the first part of this video lecture, we saw that a statement of a proposition saying if a sequence of random variables converges in probability, then it converges in distribution to the same limit. And we have also stated another proposition that says convergence in distribution implies convergence in probability in one particular case. That's when the limit is constant almost surely. We have proved that proposition, and we have collected together all these propositions and theorems we have proved so far to get the complete diagram of implications in the case of a probability space. For measure spaces, it will be a little different, and we are not doing it here. And in this video lecture, we are doing these two implications here. In the previous video lecture, we have already proved this one, and now we are going to prove this one. Convergence in probability implies convergence in distribution. And in order to prove this, we are not going to use the definition of convergence in distribution. We're going to use a theorem which says convergence is this convergence will in distribution is equivalent to convergence of this expectation here. If the expectation of f of xn converges to the expectation of f of x as n tend to infinity, and this is true for every bounded continuous function f, that means that is equivalent to convergence in distribution, and this is what we're going to show, because then it is much simpler to show this. And the proof will be the following. We start like we did in the last video lecture that had this nice touch of doing arguments by subsequences. We start by supposing that xn converges almost surely to x, and well, since f is continuous, then the set of omega for which this sequence of numbers converge to this sequence, to this number, x of omega, well, because f is continuous, this implies that f of this sequence of numbers will converge to the sequence, to this number, f of x of omega. And because the probability of this event here is 1, and this event implies this other event, we have that the probability of this event is also 1, which is the same as saying f of xn converges almost surely to f of x. Now, since f is bounded, we can use dominated convergence theorem, and f is bounded, which means all these random variables here, they are bounded by a constant, and constant on a probability space is also always integrable. We can use dominated convergence theorem with a constant function g, constant equal to this number here that serves as an upper bound for all these functions f, and we can get this above convergence. Which one? We can prove this convergence here. We have proved this convergence for any given function f from reals to reals, which is bounded and continuous. So this already implies, we have already proved that xn, if fxn converges almost surely to x, then expectation of f of xn will converge to the expectation of f of x. But now, suppose xn does not converge almost surely to x, instead it converges in probability. How can we go around that? Well, we do what we did in the last video lecture about the subsequence argument. We take a subsequence, x and k. We know it still converges in probability to x, and we want to show that any subsequence of it, that it has a sub. So we have proved that for any, assuming xn converges in probability to x, we have proved that for any continuous bounded function f from reals to reals, we have this convergence of numbers here, and this is the same as xn converging in distribution to x, which concludes the proof of this proposition therefore concludes this video lecture and this unit.